All right. All right. So, hello, everybody. I am Mariah Sinclair. I am the Senior Education Specialist at the National Radio Astronomy Observatory in Charlottesville, Virginia. My background is in education. I was a high school science teacher. And so I will be honest, I am not used to sitting and talking. I am used to being up and moving around. And so you will probably see my hands flailing. I apologize for that. But the focus of my talk today is incorporating radio astronomy into the classroom and specifically focusing on the Very Large Array, because that would be our telescope that is nearest in the continental United States. Okay, we are not. Well, we already have and I went too far. Okay. All right. So the National Radio Astronomy Observatory enables forefront research into the universe at radio wavelengths in partnership with the scientific community. We provide world-leading telescopes, instrumentation, data, and expertise. We train the next generation of scientists and engineers. We advance broader, equitable, inclusive participation in science and engineering and promote astronomy to foster a more scientifically literate society. That's our lovely mission statement. A little bit of history on the NRAO. We were founded in 1956 in Green Bank, West Virginia. It was the nearest location to Washington, D.C. that would facilitate radio astronomy. It was the first national science facility. It was built to compete on a world market. So the goal was to provide scientific community with the best radio telescopes in the world. The Green Bank Observatory is still in existence, and it is now a scientific and engineering village in the middle of the radio quiet zone, which is this 13,000 square mile area with limited radio interference. And we will talk about that a little bit later. And it is home to the Green Bank Telescope, which is the world's largest fully steerable and most accurate single dish radio telescope. It's has a 100-meter diameter dish. It weighs 17 million pounds, and it is 485 feet tall. So it's a pretty large telescope. The National Radio Astronomy Observatory is funded by the National Science Foundation. So we are your tax dollars at work. We are your observatory. We are managed by Associated Universities Incorporated. NRAO currently operates 3 major observatories. There's ALMA, which is the Atacama Large Millimeter Submillimeter Array, the VLBA, the Very Long Baseline Array, the VLA, the Very Large Array, and then NG-VLA, which is the Next Generation Very Large Array. And you will notice the very clever scientific names that come into play in naming our telescopes. There's 2 other locations that NRAO operates. Here in Charlottesville, we have the Central Development Laboratory, which is our engineering facility. It builds the receivers that are all used on the ALMA telescope. And we also have the headquarters for the National Radio Astronomy Observatory, which is where I work, which is just a bunch of boring offices. Okay, so let's talk about these telescopes. We have ALMA. The lovely ALMA is an interferometer. And for those that aren't familiar, an interferometer is a group of antennae that work together to act as one very large telescope. Green Bank telescope is 100 meters in diameter. ALMA has 66, 12, and 7-meter telescopes that work together. So in essence, it's actually larger than the Green Bank telescope. It's located in the Atacama Desert of northern Chile, which is the driest desert in the world. Radio waves are not a fan of rain and humidity, so we refer to our locations as being high and dry. We try and put our telescopes in the highest and the driest locations possible. ALMA is located at an altitude of 16,000 feet, and we refer to that as the high site. And if you are ever interested in visiting ALMA, getting access to the high site actually requires doctor approval. You have to have oxygen to get there. It's worth it, but there's quite a few hoops because of its location. ALMA is actually a partnership among Europe, the US, Canada, several countries from East Asia, and the Republic of Chile. And ALMA has been fully operational since 2013. The primary science for ALMA is molecular lines. It is studying the chemistry of objects in space. And so this is giving you an example of a spectral scan survey of a nearby starburst galaxy. Okay, now we've done that again. Some other science that ALMA is involved with is cosmology and the high redshift universe. So that's studying and proving that the universe is expanding. ALMA looks at star formation, galaxies, galactic nuclei. The image on the right there is of planet-forming disks, and it also looks at stellar evolution. The VLBA, the Very Long Baseline Array, is another interferometer. It has 10 identical 25-meter telescopes. It's a transcontinental interferometer. Its baseline at its largest part is over 8,000 kilometers apart. It spans from Mauna Kea, Hawaii to St. Croix in the Virgin Islands. And then it has 8 other dishes that are scattered throughout the continental United States. All of the antennae are controlled remotely from the Science Operations Center in Socorro, New Mexico. The VLBA, because of its extended array, it's able to provide some ultra high resolution images. That picture on the bottom right is a radar picture of the moon. That's the Tycho crater, and it's about 108 million years old. That image was taken by transmitting from the Green Bank telescope, and the data was received with the VLBA, and it's the most detailed image of the crater that exists. Some other things that the VLBA is doing is it's studying Earth's orientation and the proper motion of objects in comparison to the galactic center of our galaxy. And then we get to the VLA, and the VLA is our okay, I'm getting ahead of myself, sorry. So the VLA is an interferometer. It has 27 25-meter telescopes, has one backup telescope that is usually hanging out in the barn. The VLA is located 50 miles west of Socorro, New Mexico. So it's about halfway between Las Cruces and Albuquerque. It's located on the plains of San Agustin at 7,000 feet, and it's surrounded by mountains, again, high and dry, limited population. Construction began for the VLA in 1973. It's been operational since 1978, and it was fully commissioned and going in 1980. In 2001, it was updated, and that update took about 11 years to complete. Each antenna of the VLA is about 90 feet tall and weighs 230 tons. The VLA can see 82% of the sky. The rest of the sky is too far south. The coolest part of the VLA is it's actually laid out in a Y shape. So it has north, west, and east arms. There's over 80 miles of railroad track that allow the dishes to be moved or configured. There's the A, B, C, and D configurations. And we actually have a special transporter that was built specifically to move the antennas. So these different configurations, the A configuration, when the telescopes are in the A configuration, the best way to think of this is they are a long way away. That would be the largest diameter of the interferometer, and it would in essence be a 22-mile wide telescope dish. The B configuration is 7 miles in diameter. C configuration is 2 miles in diameter, and then the D configuration is when they are closest together, and it's only 6/10 of a mile in diameter. The reason why those configurations matter is because of the image that we're getting, the data that it's receiving. So the A configuration gives us the highest resolution. The D configuration is actually the greatest sensitivity. As you can see in those different images, you're seeing a larger picture, you're seeing more detail, but it's not a very clear picture. It's very fuzzy. The B configuration is kind of a balance between the two with the resolution and sensitivity. A configuration is our most requested configuration. So A is the majority of proposals that come in want the A configuration. On our website, we have a tracking of what configuration the VLA is currently in and what configuration it will be in, and you can actually see when it's being moved, which is an amazing site. So some scientific discoveries from the VLA. The VLA actually discovered that there is water ice on Mercury. You would not think that the innermost planet would have ice, seeing as its surface temperature is approximately 425 degrees Celsius, but we found ice. In 1991, a 8.5 gigahertz microwave beam was sent from an antenna in Goldstone, California. It bounced off of Mercury and we collected it back at the VLA. The resulting radar image showed strong reflection at Mercury's North Pole, and that resembled the polar ice caps of Mars. Normal ice absorbs radio waves, but ice at very low temperatures reflects radio waves. And this ice is in these deep recesses. So not something you would think of, but Mercury has polar ice caps. Another scientific discovery, Hercules A. So Galaxy 3C 348, relatively normal elliptical galaxy. It's in the constellation Hercules. In radio, you see jets that are over 1 million light years long. So those jets, those plumes of gases that are in that image, that's over 1 million light years long. It's more than 1,000 times. The galaxy itself is more than 1,000 times more massive than our own Milky Way, and its black hole is nearly 1,000 times more massive than our own Sagittarius star. Our black hole is relatively quiet, while this black hole is actively eating, which causes these large gas eruptions. We don't really understand how these jets form. We just know they're there. And we didn't see them until we looked at the galaxy with a radio telescope. HL Tau is a young star, it's very young in terms of the age of our universe. It's only about 1 million years old. It's in the constellation Taurus, which is approximately 450 light years away. This image is actually a composite. The red was taken by ALMA, and then the yellow, that inner part, is data from the VLA, and it shows the star and its protoplanetary disk. The neat thing about HL Tau is those gaps. So the gaps in the rings are caused by young planets that are forming around that star. This image helps us understand how planets form, and it shows that it happens faster than we thought. One of the goals of NGVLA is to study the formation of solar systems. Then we get to VLAS, or the VLA Sky Survey. So the 4 configurations, A, B, C, and D, there's actually kind of a 5th one. We can take the telescope and combine A and B together, and they use that for this sky survey. So what they're doing is they are actually mapping the radio universe. It's taking 8 years. It's been going for a couple of years. I think it's actually getting near to completion. But they are scanning the sky. They're going to scan it 3 times, and they're compiling a catalog that will have approximately 10 million radio sources. This catalog is, of course, open source. All of our data is open source. And if you go to our website, you can go to our VLA link and look and see the data that has been gathered. All right, so now our next one, our next generation very large array. So the VLA, when it was built, was leaps beyond any radio telescope before it. NGVLA is going to continue that tradition. It will be another interferometer that will span from Hawaii to the Caribbean. It will actually be an array of 263 radio antenna. Again, it will be centered on the plains of San Agustin. So the headquarters will be there in Socorro, New Mexico. It will have a resolution 100 times greater than the VLA with 10 times its sensitivity. So if you think back to those pictures where we looked at the A configuration and how clear that was compared to the D configuration, imagine that image as seen with the NGVLA, where it's 100 times greater resolution. The NGVLA will let astronomers see fainter objects than ever before and in greater detail. It will reveal mysteries about supermassive black holes that lurk in the hearts of galaxies, how planets form around young stars, and even the complex chemistry in vast interstellar clouds of molecular gas. When constructed, the NGVLA will be the radio telescope for the next generation of astronomers, and construction is expected to begin within the next 10 years. So why radio astronomy? Why do we care about this? Why is it so important? So this image right here, this is the Crab Nebula. If you were to go out and look at the Crab Nebula, this is what you would see. This is invisible light. The Crab Nebula, it's a supernova remnant. It's the end state of a star that was many times larger than our sun. Crab Nebula was observed originally by the Chinese astronomers back in 1054 when the explosion happened. At that time, the supernova was visible during the day. It's been cooling and fading for nearly 1,000 years now. No longer visible during the day. Visible light is only a small part of the electromagnetic spectrum. If we look at the Crab Nebula in radio waves or in infrared or in ultraviolet or in X-ray, we get a much larger picture. We get a more complete picture of what is actually going on in that nebula. So this image is a compilation using 5 different telescopes. You have the VLA using radio waves, Spitzer using infrared, Hubble is the optical, XMM Newton is the ultraviolet, and then Chandra X-ray, obviously the X-rays. When we compile all of that data together, we finally see the complete picture. If we only look at it with an optical telescope, we don't see any of the other stuff going on. So this is why radio astronomy is so important. This is why all of the electromagnetic spectrum is so important. Visible versus invisible light. How do we incorporate radio astronomy into the classroom? So this electromagnetic spectrum, visible light is less than 1% of light energy, meaning we can't see 99% of the light energy. There are other animals on our planet that have better eyesight than we do. You have snakes that can see in infrared and bumblebees that can see ultraviolet. For us humans, this visible light, it really limits us. So by having telescopes that are able to see in these other forms of light, we get that whole picture. Here we have the Milky Way. This is an image of the Milky Way. That 1% optical is vastly different than if you look at it in radio or infrared or in gamma rays. So depending upon the light energy we look at, we get more information. Here's a better example. So this is our Milky Way. It's beautiful. Go out at night. It's gorgeous. Here's our Milky Way in radio waves. In radio, the amazing thing with radio can see hydrogen, and hydrogen is what makes up our universe. It is the most abundant gas in our universe. Here's another example. Here's that Crab Nebula. Optical, there it is in radio. So again, we get a greater picture. We get more information about what's actually going on. This is probably one of my favorite ones. So this is an optical image taken with Hubble, I believe. Here's what's actually going on. If we look at this in radio, we see again those plumes of molecular gases. If you just look at it through an optical telescope, you have no idea of what's going on. You just see the light, the visible light. So what are these wavelengths and what can we see with them? With radio waves, we see electrons moving in magnetic fields. We see molecular gases. Microwaves show cosmic microwave background. Infrared, this is your young stars, your low mass stars, your planet and star formation. Optical, your nebula, your stars, your galaxies. Ultraviolet is your hot stars, your high mass stars, your solar corona. X-ray will show you your supernova remnants, your black holes, your hot gas plasma, and then gamma rays, your gamma ray bursts, your compact objects merging. Again, it's all of those working together. You have to have the different telescopes working together to get the full picture because objects don't just have one form of energy. Okay, so who uses the electromagnetic spectrum? As you can see, this list, it's pretty long, and I cut it down short because I didn't have enough slides. We've got cell phones, internet. Anybody have a robot vacuum? My Roomba loves the Wi-Fi. Weather forecasting, your garage door openers, TV, radio. Everyone uses the electromagnetic spectrum. This is the United States frequency allocations. And as you can see, it gets really gobbledygooky down there. Where this comes into the classroom is, I'm getting ahead of myself again. I'm sorry. All right, so radio frequency interference. Radio waves are not sound waves, and this is a large confusion. All of those objects using the electromagnetic spectrum make a lot of noise. But again, radio waves, not sound waves. So when we say noise, think of it as glowing. Jodie Foster, Contact, she's our role model. She's the hero of the VLA. This scene from Contact, not scientifically accurate. There was nothing for her to listen to. The radio waves that we get from space are incredibly weak. When we have radio waves from cell phones, microwaves, radio and TV stations, they basically are screaming. They are just pounding our telescopes with these waves. And that makes it so our telescopes, it's almost impossible to detect the radio waves from space. One of the things we like to say is that RFI is the radio equivalent of light pollution. So everyone using the electromagnetic spectrum kind of makes it so our radio telescopes are at a disadvantage. Because one of the advantages that we have with having a radio telescope is that they're ground-based. They don't have to be up in space like James Webb or Hubble, because radio waves are able to pass through our atmosphere. Unfortunately, as humans keep inventing fabulous technology, as I sit here on my laptop in my kitchen using Wi-Fi, nearby telescopes, it interferes with the data they're receiving. So that does become an issue. All right, with that, I have run through this really quickly. So I am ready to stop sharing my screen and let's talk. Any questions anybody has, anything I can answer, that would be great.
There is at least one question in the text chat, Mariah.
Let me move this over. I minimized this and now I can't get to the chat.
I suppose I can read them if I need to, but it'd be, I suppose
No,
it'd be good if you can get
I
them.
got it here. I
Okay,
got
cool.
it here.
We got two questions in chat, and then Arwen's raising her hand too.
Is ALMA part of the EHT? Yes. So ALMA is part of EHT. The VLA has been part of EHT. It depends upon the project. ALMA was involved with that amazing picture of the event horizon on our sorry, I'm still messing with my computer here, of the event horizon of Sag A star, of the center of our galaxy. Yes, it depends upon the project. Many times you had these telescopes working together. Okay. And then how do you deal with gravity lensing? So Einstein rings, basically like the VLA, it's not that they're necessarily, and again, first off, I'm not an astronomer, but my job is education. So my information, correct me if I'm wrong, but from what we've used the VLA to prove Einstein's rings. But from what I understand, I've never seen anything that there's been an issue with the gravitational lensing. I could be wrong on that. So I don't know. Is there education link for the VLA? Yes, and that's the second part I was going to, I should have shared at the beginning here a Google Drive that has this slideshow, and it also has links to resources we have. And I wanted to walk you through, I wanted to show you some of the, there, perfect. Some of the resources that we have available online. And then the person that has their hand up, somebody else speak besides me.
Okay. So you
Hiya.
okay, let me task it, okay? We have a guest today. So when you were showing us the pictures earlier of different types of light, right? So we have optical and we have radio and all of that.
Not my sister.
Hey, stop, Reese.
I
Let me
don't
ask.
want.
Okay. With radio, is there a standard for what colors we use to represent the wavelengths in visible light?
There is. And again, what we have to, the thing that nobody likes to know is that the majority of the images, like my favorite image, and I'm going to share my screen again here real quick. So this right here, the Manatee Nebula, fabulous image of, and this is a radio image, that it doesn't really exist in real life. It's, our images that we have, they're data. And that's one of the educational resources I have is our data analysts, we get this data in and they turn this data into graphs to look for anomalies. And it's when they see these anomalies that they go, oh, there's something there. And then we have artists. We have a visualization team that then converts that into something that the public would go, hey, that's kind of pretty. I'm interested in that. Because if we just put out the data, the public is going to go, well, that's kind of boring. So, but yeah, so like the Manatee Nebula, beautiful as it is, it's not a real, that wasn't actually seen that way. I don't know if the images, the coloring is standard. We try and have a set standard throughout our observatories solely for our outreach. But if you noticed, and I don't know if you caught this, I caught it as I was making the slides, the Crab Nebula image that I showed that was just optical was in yellow, but then our latest graphic that has the Crab Nebula with all of the 5 telescopes, they're now using green for optical. So they have changed the coloring. But we usually have that radio is, because of the filtering we use, that radio is red, whereas others are blue. So that's kind of the standard across our observatory. I hope that helps.
But yeah, no, that's wonderful. But so it sounds like there isn't a one-to-one between this wavelength and radio is always going to be represented by this color in optical.
No, because you're
going to be depending on the observatory and
Yeah.
the artist bringing that out.
Because the colors are based upon that visible light spectrum, which are in that 1%. So there's not a color representation for those other wavelengths. So that's where you have that artistic license that comes in.
Okay, thank you for that clarification. Yeah.
And we had somebody asked about detecting pulsars accurately. Yes, pulsars are a huge thing. We have pulsar. There's all kinds of research done on pulsar. We have what's the name of it? It's actually an organization for high schoolers, the Pulsar Search Collaboration, I believe it is, where high school students are using radio telescopes to search for pulsars. So yes, and it was radio that discovered the first pulsar. And I have lost the name of the person that made that noticed and was like, wait a sec, we've got something, why is this, what's going on here? So other questions, any other questions? There we go. That's nanograph, that's not us. I'm kidding, you're good.
Oh, is there another one, or you guys have your own
I
page
think
with the
so.
same collaborative?
And I don't know, and it might be, I haven't been involved with the Pulsar group for a while. They might have combined them recently. So especially nanograph, it could be that that's the same. It could very well be the same now. We all work together.
That's probably what it is. Here's one on the. Well, no, that took me to nanograph too. Never mind. I'll keep looking.
Yep. So it's got to be that it's now a collaboration between that it's theirs. So yes, Paul, question?
Thank you very much indeed for your presentation, Maria. That was fascinating. No more of an observation. From the UK, we've had a go at doing is it Radio Jove projects.
Mhm.
So that's something that people are familiar with and would rate. It's good for listening, not just to Jupiter, but also in this day and age, the sun, solar activity has been really active recently, and get lots of really interesting data to analyze about the solar flares. So would highly recommend that if anyone else is interested. Really simple kit set up, lovely project to do with the pupils. So just flag that up to anyone who may be interested.
No, that's and one of the activities that I've got in the Google Drive is a truncated, and it's taken from Radio Jove, and the final data that the students would graph is solar storms. So yes, exactly. Yeah, and Radio Jove is fabulous. It's such a fabulous, so yay. And it's kind of an older project. So I'm glad to hear that somebody's still, and especially, I would imagine that right now, especially with, what was it, last week when the sun was like, hey, I'm here, don't forget about me. You guys got some amazing data. Anybody else? If I can share again real quick, I will show you we've got is there a thing like helio radio imaging? I'm not sure. That's a good question. I don't know. And is Green Bank planning any collaboration with the LISA folks? So Green Bank, I don't know. Green Bank is kind of separated from NRAO, but they are still a part of NRAO. It's a weird, it's kind of like a redheaded stepchild sometimes. I don't know. They're a part of us, but so I don't have full information on what's going on with Green Bank these days. They're a part of NSF and they're coming back into NRAO, but currently we don't have direct. So I don't know what their science is going on right now. I know that Green Bank is still doing the breakthrough listen, they did the stuff with like LIGO and nanograph, but I'm not sure now what's going on with all that. So I don't have a good answer on that. So, okay, so if I can just, let me pull up here. So we have on our website under the Explore tab, we've got two things that would be excellent for a classroom. The first one we have is this cosmic coloring compositor, and it enables students or adults that we've got several different objects, and you're able to go through and turn on the different types of light energy and color it however, whatever color you would like, and you're able to see what is visible in that object in the different light energy forms. So it's a great way to experiment and understand more how we see what we see in the different forms of light energy. And then the other that I wanted to show you, we have a link to interferometry explained, and it allows students and adults, I can make this bigger, sorry, you choose a source, you choose an image, and you are able to change the location of the dishes. You can make your interferometer be bigger or be smaller, and to see how the resolution of the image changes. So those are just some really great, especially for a classroom. We then, of course, have the VLA Explorer, which goes into detail about different parts of the VLA, just quick, less than a minute long videos. We've got one on ALMA and NRAO mission control. The other thing that's in that Google Drive that I shared with you, there is a blanket letter that explains the next generation science standards that correlate to the assignments. And then there's some assignments, some different activities that we've created, one of which, this is our latest, and this is the funnest. It's a do-it-yourself Faraday cage for cell phones, because cell phones have become such an issue in the classroom as a distraction. And basically all you have to do is you wrap your cell phone in tinfoil, and it can't receive it's not going to get any text, not going to get any Snapchats. So kids are able to make their own Faraday cage, and teachers get a little bit of a peace of mind. And I've got some follow-up activities in here, testing it with a handheld radio. You can experiment with different foil amounts. One thing I learned, if you use Costco's pre-cut foil, it's got perforations in it, so you have to use at least 3 sheets of foil. So don't get Costco's pre-cut. It does not work great. And then you can also, you know, for talking about how Faraday cages work, try with different construction materials. Try with copper mesh or different fabrics. At the Green Bank Telescope, one of the nifty things they do when you go on the bus tour, they used to have a Pringles can that people would put their Fitbits and their smartwatches in, because a Pringles can is lined with foil and it acts as a Faraday cage. Also in here, we've got, this is the graphing radio signals. So this is the activity I was talking about that is taken from Radio Jove. And it talks some basics about radio astronomy. And then you have, this would be storms on Jupiter. And then it talks about how to take that data and graph it. And this is based on a solar storm. The other things that are in the file that I've shared with you all, this make your own radio image is taking data, the pixelation form like our astronomers get, and coloring your own radio image. And you would make a color map. I believe this first one is a spiral galaxy. I believe, I think it's this first image. We also have an activity on making your own spectroscope using either a diffraction grating or an old CD-ROM. And you just take a piece of black paper, cut this pattern out, make sure to put a slit, and you put the diffraction grating at the other end, and you've got yourself a fabulous spectroscope that you can point at white light to break apart to see all the different colors. Modeling radio astronomy. This is a fun activity where you have one student hold an umbrella upside down, and you have other students that have different colored ball pit balls that you use to model radio waves, or all the different waves being emitted, and they toss them and try and get them into the umbrella. And then you count them and graph that. So a graphing activity, and they see that all these different types of wavelengths are being caught by the radio telescope, and but not all, the radio telescope doesn't catch all of them. And one of the things I love to do with this activity is I blow up a giant beach ball and I throw it at it kind of in between, and I use that to model a cell phone being around a radio telescope. So I think that that's the essence of the activities that I was going to share with everybody. Excuse me. So let's see. Okay, so okay, so back to the questions on the EMP. Are all the telescopes hardened in case? So on the telescopes, the majority of our receivers are cooled using liquid helium, so that the noise, the background noise, isn't picked up by the telescope. All right. I didn't put anything in here on the receivers and all of that. So, okay, let's see what else. What am I missing here? Okay, global darks, can the telescopes be repositioned to transmit to each other and act as a relay and repeater? So our telescopes are used in like radar. You know, most people think of our telescopes as being receivers, but they do, like we mapped, the Green Bank telescope was actually used to, it mapped the surface of Venus years ago. So they are able to transmit along with receive. Okay. Anything else? Are there other questions? I feel like I've talked a lot.
No, that was great stuff, Mariah. Fantastic that you talked all that. Other questions for Mariah or anything relevant that you want to share? We do have a few minutes. Mariah,
Oh, I
are there
what?
sorry, are there any events coming up or programs that educators should be aware of that they could potentially take advantage of?
So there's Green Bank has Ping, which is is a summer camp for ninth graders, but I believe that date has already closed.
Hmm.
But that's for so eighth graders during their eighth grade year, they can apply to be in the Ping camp. And you spend 2 weeks at the Green Bank Telescope. And the Green Bank Telescope has they're a fabulous place for educational opportunities. They have the 40-foot telescope, which is a teaching telescope where people are able to go, students, specifically student organizations, be it high school, be it colleges, and you do a hydrogen scan.
Wow.
It's this older telescope and you scan the Milky Way for hydrogen, and you are able to see by this data that you get the movement of the Milky Way and the location of the Milky Way. So Green Bank Telescope is great if you're on the East Coast. If you're on the West Coast, the VLA every Saturday has guided tours. The VLA is open Monday through, they're open 7 days a week from 9 a.m. to 4 p.m. They're self-guided tours all the time. We also have, there's my counterpart, Vanshri, is at the VLA in New Mexico, and she does educational programming there. And so if you have an educational group, you can request a private tour, and she will make programming specific to your group. So several options. For me, myself here in Charlottesville, you can come see my boring office if you want.
Love it. Yeah, I think it'd be amazing to visit the VLA or
It's
any of these sites.
When the VLAS is doing the survey, you can actually see the telescopes, like, because they constantly are moving. It's like every 3 seconds, and you can see them kind of doot, 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 doot. Supposedly, I've never seen it, but supposedly it's pretty nifty. So
If I'm doing the math right, everybody, we got about 10 more minutes. We will be close to VLA in October.
so the VLA in October, we have open house in October. If you're there, that's
when
a
is
big
that?
event. So it's October is the third Saturday, I believe. It's either the first Saturday of October or the third Saturday of October. So the wobble of the Earth, that was actually detected with telescopes in Green Bank. They used the interferometer. They had 2 telescopes there, and there was a third one that I believe was at Sugarloaf, that was used to measure the wobble of the Earth. And I think I'm out of trivia.
Is there a place people can find that open house, or is that on this visit us page maybe?
Yes, it should be on the Visit VLA upcoming events. We do open house in April and in October, and the open house has guest speakers. There's scientists that speak. There's food trucks. That's my favorite part. There's all kinds of activities. There's educational activities. There's crafts for kids. It's free. There's no charge to attend on open house. And open house correlates to Trinity Site's open house. If anybody saw Oppenheimer, it's on the same day that Trinity Site is open.
Awesome. Other questions for Mariah or other topics you guys might want to delve into? We do have 10 minutes. Mariah, are there any opportunities for students to get access to? Well, I guess you were just telling us about one at Green Bank. But are there opportunities for students to get access to telescope data?
So all of our data is open source. And after a year, it's published and anybody can have access to it. Also, anybody can request, put in a proposal to use the telescopes.
Oh, wow.
We get tons and tons of proposals, but if it's a good proposal, it's not that our telescopes are only used by NRAO staff. Anybody here, anybody is able to put in a proposal to use the telescopes. We have, there's several different programs. We have programs specifically for college students. We have like the NAC and the 9, which are for the underserved population, specifically in astronomy. We also have like right now, we just got our summer students. There's always summer students that are at the observatories and in the buildings doing research programs. So those are going to be your graduate students in astronomy. For the general population, there's not necessarily we get requests often for like high school interns or high school projects, and we don't really have anything set up for that, mostly because of the type of astronomy that's being done. You have to have a pretty strong physics background. And so that makes it a little bit difficult to tailor research to those that are younger. Green Bank is, they're just in a lucky position that they had that old telescope and they were able to figure out hey, we can use this for a simple hydrogen scan. That just worked out really well. We have at the VLA, it's called the Spider, and we're hoping to get that up and running and online. And then you could do remote scans. There is a telescope, I believe it's out of Greece. It's called Pictar, and it's a radio telescope that anyone can go on and do scans, and it does great. You can do the hydrogen scan and you can see like when the Milky Way is overhead. The issue that you have is, it's not remote. So you're dependent upon the Earth's location. And so you just have to pay attention to the time and set your scan, go in and do your scan when the Milky Way is going to be overhead. So yep, that's it, Pictar. And that's great fun. It gets great data, and data that kids they can see how radio data is collected.
Wow. So they can make a request remotely? Is that how?
No, you just go in and you just do it right then and there.
Wow.
You just log in and you click scan, and it sends you an email with your data. And the data is in a graph form. It's also got more detailed data, but the graph, if it's when the Milky Way is overhead, you see the serious hydrogen spikes, so you can look for that high line.
Wow, yeah, I'm gonna try that.
Yeah, I just kept getting confused on what time it was, the time zones.
Awesome. We got about 5 minutes left. Anybody else have other questions for Mariah? If not, if you guys want to adjourn to the large room, I imagine conversation will begin to develop there before Frank is up. Frank and Christina are up at the top of the hour. So we got about 20 minutes till that closing capstone fireside chat. But yeah, thank you, Mariah, for coming and sharing all those resources and sharing so much information about the various arrays.
Yeah.
Thank
Can
you
I
for-
ask a quick question? I tuned in late or got into the room late. How did you get motivated and excited about this? And perhaps you already discussed this before my arrival, but
No, that's a great question.
your interest in and how you are where you are today.
No, I grew up in Las Cruces, New Mexico, which is where Clyde Tombaugh lived. The telescope that he built that is what he discovered Pluto with. He lived on my street, and he was just this little old man that would walk down the street, and his wife made really good brownies. But so astronomy in New Mexico is just, it's part of it's your world. And I was a high school science teacher. I taught chemistry and biology and astronomy just because I was interested and loved it. And then I saw this job posted and I applied for it and I got it. And so now I get to share with kids my love of astronomy. And that's yeah, it's a dream job.
Awesome. Thank you.
Man, that's
Thank
awesome.
you.
And kids have the opportunity, by the way, to do the Clyde Tombaugh quest on SLU, where you sort of rediscover Pluto using his methods.
Oh, that's fabulous.
Yeah.
That's fabulous.
It's one of the ones I've gone through myself. It's really, really quite cool.
That I mean, I understand, that his wife, after he passed away, they donated his telescope to the Smithsonian. It's in the Smithsonian now. But it was always kind of like, wait, no, this is the neighborhoods. What do you mean? We have to share it with other people? What? No. But yeah, you kind of take for granted stuff when you're, that's in your backyard.
Oh,
But
for sure. That's awesome. You remind me actually of Andy Aldrin's stories. People always ask him, like, is it strange growing up with your dad as an astronaut? And he's like, no, like everybody on my street, their dad was an astronaut.
yeah, yeah. That's great.
Yeah.
Well, thank you, everybody. You guys have been a fabulous audience. I really appreciate this. And great questions. Thank you so much.
Awesome. Thank you again, Mariah. I will stop the recording and I will see you all in the big room for Frank's capstone.